In this section, we're going to look at some special factoring cases, and we're going to be able to identify how to know when it's a special case of factoring. Let's look at our first example here. We're going to factor 9x squared minus 1. Now, right off the top of the bat, notice that it looks different than the other factoring we've been doing. In the previous sections, we were looking at factoring trinomials, which has 3 terms. Before that, we were looking at factoring by grouping, which has 4 terms. So one of the ways to identify which kind of factoring that we're using is to simply count the number of terms. Notice in this case, we only have 2. Very different from what we're used to. So, first of all, count the terms, 1, 2. Secondly, see what's going on with the numbers. In this particular case, notice that 9x squared is a perfect square. In fact, 9x squared is 3x times 3x. Similarly, 1 is also a perfect square. 1 times 1 is 1. And notice also we have a minus sign between the 2 terms. This special case of factoring is called factoring the difference of 2 perfect squares. Factoring the difference of 2 perfect squares, how do you identify it? First of all, look for the minus sign and check to make sure that both these are perfect squares. Once you identify this, then it's so easy to factor. Put down your 2 sets of parentheses as usual. This one, remember, is 9x squared, which is a factor of 3x times itself. So what goes in our parentheses? 3x and 3x. We know here that that 1 is 1 times 1. So what goes in here? 1 and 1. And the signs are always opposite. Plus 1, minus 1. So when you see 9x squared minus 1, first of all, count the number of terms, 2. Check to make sure there's a negative sign. Check to make sure that both those are perfect squares, and it factors into this pattern, 3x plus 1 and 3x minus 1. You'll find that the more you work at this, the more fun you're going to have. Let's try the second one, 4x squared minus 49. Again, count the number of terms, 2. Minus sign, check. Perfect square, check. Perfect square, check. So again, this is the special case of factoring the difference of 2 perfect squares. We put them in the parentheses. This is the fun part, 2x plus 7 and 2x minus 7. Would you agree that this is probably the easiest kind of factoring we've done thus far? I think so. Now let's see what happens in our next case down here. X to the 8th minus 1. Now, that may be difficult for you to recognize, but x to the 8th is actually a perfect square. In fact, if we go back to our exponent rules, x to the 4th times x to the 4th is x to the, remember this rule? When we're multiplying monomials, we're going to add those exponents. 4 plus 4, 8. So in fact, x to the 8th is a perfect square. It's x to the 4th times x to the 4th. So again, 2 terms, perfect square, minus sign. We have the special case of factoring the difference of 2 perfect squares. So this job is easy. Put in the parentheses. This factors into x to the 4th plus 1 and x to the 4th minus 1. But don't stop there. This problem happens to be twice as fun as the others. Why do I say that? Because look over here. Look what we factored the second factor into. We've got 2 terms, 1, 2. We've got that minus sign. We've got a perfect square, and we've got a perfect square. Well, you might be asking yourself, x to the 4th a perfect square? Yes, it is. Just like x to the 8th was, x squared times x squared is x to the 4th. So certainly x to the 4th is a perfect square. So what do we get to do to this now? Well, we get to take the second parentheses there and factor one more time. Now, you might be asking yourself at this point, well, wait a minute. These two look very similar. Doesn't this first one factor as well? Think about it. What are the conditions that we need to factor the difference of perfect squares? We need to have perfect squares, which we do, but don't forget, we need the minus sign. In this case, there's a plus sign, so this does not factor any further. So this first one remains as x to the fourth plus 1. And keep that in your mind because that is a common error. Many students would like to factor this one as well, but don't do it. All right, so here we go. And we factor this into x squared plus 1 and x squared minus 1. Now, do you think we're done? You're right, we're not. Look down here at the end. What happened? We know that we cannot factor these because these are the sum of perfect squares. But look at the very end. What did we create for ourselves again? We have here the difference of perfect squares. So we're going to have more fun. Now again, these two remain the same because these are the sum of squares which do not factor. That is not a special case of factoring. But down here at the end we have another special case of factoring. This is going to factor into x plus 1, x minus 1. Now, are you saying to yourself, when is this going to end? How do I tell? Well, look over here. We're down to x minus 1. Does that factor again? Remember the rule. We have the minus sign, but do we have perfect squares? X, notice, is not a perfect square. So because it's not, we cannot factor this any further. We have to stop our fun at this point. This x to the 8th minus 1 factored into x to the 4th plus 1, x squared plus 1, x plus 1 times x minus 1. This is the complete factorization for this x to the 8th minus 1. If we would have stopped anywhere between the beginning here and the end, for instance, if you thought, okay, this is your final answer or this is your final answer, you would be incorrect because this would not be considered completely factored. Only this final line here is the complete factorization of x to the 8th minus 1. So again, the special case is called the difference of two perfect squares. How do I identify it? First of all, I count the number of terms, 2. Check for the all-important minus sign or subtraction sign. Check to make sure that both those terms are perfect squares and have fun with it. Let's look at some other special cases of factoring. We're going to factor here 16x to the second plus 8x plus 1. When you first look at that problem, you may not think that looks like anything different that you factored before. In fact, you probably think you want to factor because it's a trinomial and possibly use the trial and error method or perhaps the grouping method by playing the product sum game. Well, if we look carefully, though, at this problem, we'll notice it's a little bit different. Notice the first term here, 16x squared, happens to be a perfect square. It happens to be 4x times 4x. Notice this one here happens to be a perfect square. It happens to be 1 times 1. And notice if I multiply these two together, 4x times 1, and then double it or multiply by 2, I get the middle term 8x. That's what's going to make this into a special case of factoring. Again, we look at it, we see it's a trinomial. This is a perfect square. 16x squared is 4x times 4x. This is a perfect square. It's 1 times 1. If I multiply these two together, 1 times 4x, 4x, then multiply that product by 2, I get that middle term, 8x. Now what's so special about that? If you recognize the relationship of the three terms in your trinomial, and that holds true, then you're lucky because then it simply factors into the following. It factors into 4x, which is what 16x squared is, which is 4x times 4x, and 1, because that's our 1 times 1, and since both our signs are positive, we put the plus sign, and then we square it. In fact, what we're saying then is 16x squared plus 8x plus 1 is 4x plus 1 times 4x plus 1. Now, if you don't believe me, you're saying, wait a minute, that was too quick. Let's go ahead and write it out. And remember, we can always check by foiling. 16x squared plus 4x plus 4x plus 1. 16x squared, that gives me a sum of 8x plus 1, and there you have it. So yes, indeed, because we checked by factoring, we can go ahead and write this as 4x plus 1 quantity squared. Let's look at our next case here. Now, because you see two terms, automatically I hope you're thinking something about the perfect squares or the difference of perfect squares. Well, you're correct, but the only difficulty in this one is 20x squared is not a perfect square, and neither is 45. What are we going to do? Well, don't forget the very first rule of factoring. Whenever you approach a factoring problem, always keep your eye out for a greatest common factor. In this case, between 20 and 45, we have a common factor of 5. So we're going to take out our common factor of 5. Inside of parentheses, we'll get 4x squared minus 9. Now let's see what we have inside our parentheses. We have two terms again. We have that minus sign, perfect square, perfect square. We have the special case of factoring the difference of perfect squares. So here we go, and I know you're good at this now. This factors easily into 2x plus 3 and 2x minus 3. So in these two special cases of factoring, in the first one, remember, you're keeping your eye out for a trinomial which has the first term a perfect square, the last term a perfect square. The middle term happens to be a product of whatever was squared in each one of those two, the first and third terms. In the second one here, the special factorization was, again, getting down to the difference of perfect squares, but in order to get there, in this particular problem, what we had to do is, first of all, factor out that GCF, or greatest common factor. That's probably the key rule to factoring. Always remember, think GCF.